right, welcome back. So let's go ahead and get into the processes for the zeros of polynomials. So to start off, we're going to look into finding the zeros by factoring. And if you struggle with factoring, then this is going to be a great section for you because that is all we are going to be doing is reviewing our factoring skills. And you can see I have a nice little guideline here as well. But again, if you did not already go and look at the guided notes, I have many more examples for you to go and review there as well. So let's go and take a look at these factoring techniques that we're going to want to remember. Whenever we're given, we're trying to find the zeros as well as stating the multiplicity, then remember the first thing we want to do is just set our equation equal to 0. Now again, we have more than one variable, so we can't just use our inverse operations here. We're going to want to factor. And the first thing I'd always recommend doing whenever you're factoring is always looking to factoring out a greatest common factors, something that both 3x cubed and a 3x share in common. And you can see they both share a 3x. So therefore I can factor out a 3x. And that is going to leave me with a x squared minus 1. Now our goal when we're finding the zeros is to write this as what we call a product of linear factors, or identifying the linear factorization of a polynomial. So when we're trying to find the linear factorization of a polynomial, we want all of our factors to be raised to the first power. Basically all of our x's to be raised to the first power. Now the factor can be raised to a higher power, but we want the actual variable to be raised to 1. So therefore I say, well, can I factor down x squared minus 1? And yes, using the difference of two squares, you can factor that down into x minus 1, x plus 1. Now you can see that I have a set of 3 factors, right, that multiply to give me 0. So what I'm going to do is I'm going to take each and every one and set them equal to 0. And again, I already covered this once, but again, it's something that keeps on coming up. Do not set 3 equal to 0 because 3 is not equal to 0, right? 3 is a scalar. So remember when we're setting our factors, they have to include a variable for us to set them equal to 0. And so therefore, we have 3 factors. Now notice, each one of these factors is always raised to the first power. So I know the multiplicity is going to be 1. So we have x equals 0, x equals 1, and x equals negative 1. Okay, so when we're writing our zeros, we can write them like this, and sometimes we'll also just use a solution set, plus or minus 1. Now, what I tell my students is when we're identifying the zeros and I ask for the multiplicity, as long as they all have a multiplicity of 1, you do not need to include the multiplicity. But once we start getting into a multiplicity, a higher multiplicity, then make sure that you label those zeros with that. So that's just something personally I do in my classroom. For in the next example, I can see that they have an x squared in common. So therefore, I'll just rewrite this, factor out an x squared. That's going to leave me with an x minus 3. Now, in this case, this one kind of gets a little confusing because you can't really factor that down. You can. I mean, you could factor down an x squared as to an x times x. Another way to look at this is like x minus 0 quantity squared. And the reason why I'm writing it like this is because I want you to understand the 0 of the solution to this is 0, but it has a multiplicity of 2. Because yeah, you could factor down x squared to x times x, right? And you can see it's a repeated 0. X is equal to 0 twice. That's why the multiplicity is equal to 0. So we'll have x equals 0 and x minus, or x is equal to 3, right? If you set these both equal to 0, x minus 3 equals 0, x equals 3. However, this is going to have a multiplicity of 2, and this would be a multiplicity of 1. So when I write my zeros, I'll just say multiplicity of 2. And then we'll have another factor of 3. So that's how I write them and to differentiate when the zeros have multiplicity and when they don't. The next example, again, you can see this is a trinomial. But again, just like anything else, we want to factor out the common factor. Because most students know or they remember when factoring trinomials, we don't like when there's a number in front of the x. Nor do we want this to be to the 4th power. We're familiar with factoring to the 2nd power, right? So again, first thing, let's just factor out our common factors. So that's 2x squared. So 2x squared is in common for all of them. So by factoring out a 2x squared, that's going to leave me with a x squared. Let's see, minus a 3x, and this would be a plus 2. Okay, very good. Now I see you can set these both equal to 0. So we have a 2x squared equals 0, right? And again, same thing that's happening here. X is going to equal to 0, and it's going to have a multiplicity equal to 2. Not because of this coefficient 2, but because of this power 2. Over here, I can set this equal to 0 if you don't already know what the factor is. But again, it's very important for you to recognize that is equal to 0. So again, what do we do to solve for this? We factor it, right? This is not a linear factor. To write the linear factorization, we need it to be a product of all linear factors. So to further factor this down, I get x minus 1 and x minus 2 equals 0. So therefore, x equals 1 and x is going to equal 2. So when I'm writing my solution here, I could write 1, 2, and 0 with a multiplicity of equal to 2. And again, sometimes you could write them in ascending, descending order. Just kind of depends on the question. Next example, you can see that this one is a quadratic. Cool. And yes, a quadratic, cool. But we recognize that there is a 4 in front, and that's perfectly fine. What we want to recognize, though, for this one is to be able to, again, look into factoring this. Now, sometimes it gets difficult when we have these numbers in front. And obviously, we don't want to think about the same thing, like what two numbers multiply to give you 2, add to give you -3. If you remember, that was like your technique for trinomials. Or for a quadratic. The main thing when we have a is equal to 1 is we know that that should be equal to 0. We know that the factors can be broken down into the trinomial can be broken down into a product of two binomials. And when the last two terms are going to be 1, that's going to be a positive 1, or a negative 1, and a negative 1. Now, since my middle term is negative, I know that has to be a -1 times a -1. And now what I'm basically looking for is what is going to be my common term here. This was supposed to be no, it's not 2 to the 4th. Okay. So I have an x minus 1 times an x minus 1. And then what I can say is what two numbers are going to give me a 4x squared, but will add to give me this -4. Well, if I do a positive 2x and a positive 2x, let's check our work. 2x times 2x is 4x squared. -1 times -1 is +1. And then 2x times -1 is -2x. -1 times 2x is -2x. -2x plus -2x gives you a -4x. However, what's important about this is this can now be written as a binomial squared, right? We can condense this down to a binomial squared. That's important because whatever the 0 is, which is now linear, has a multiplicity of 2. So it's already set equal to 0, right? I probably could have factored out an x. Maybe that's what I originally was looking for in this problem. Let's go ahead and actually change that because I think I wanted that to be a cube. Did I have any other cubes? Yeah, we have 4, 4, 4. Either way, let's just go ahead and, we'll just stick with that. So either way, you can take the square root of both sides, and therefore you would get 2x minus 1 is equal to 0. So therefore, x equals 1/2. But again, that has a multiplicity of 2. So there's only one answer here, which is weird because if you remember from in our previous chapter, like whatever the power was, that was many how any x-intercepts we had, right? But again, notice here, we have our solution. It's only 1, but it gets repeated. So therefore, that's why we say it has a multiplicity of 2. Probably think I wanted an x there to be factored out, but that's okay. Now let's get into a polynomial with the 4th power. Here's where a lot of students start to get a little confused because we have a trinomial and it's being raised to the 4th power. And again, when we previously had one being raised to the 4th power, we just factored out the x squared, right? And then we had something that we were familiar with. Well, here we can't factor out an x squared. So what are we going to do? The first thing I would recommend doing is forget if that's raised to the 4th power. It's a trinomial. We know how to factor trinomials when they're quadratic. So why don't we just rewrite it as a quadratic? X squared minus 10x plus 9, okay? And again, remember when you're factoring a quadratic, that's going to be a product of two binomials. So you're thinking, all right, it's going to be an x times x and x times x. What two numbers multiply to give you 9, add to give you a -10? Well, you can say, well, it's -9 and -1. Now, here's the interesting thing. If you look at this problem compared to that problem, it's the exact same numbers, right? You have a 1 for this coefficient, -10, 9. So guess what? The factoring is going to be exactly the same. The factoring is not going to change. It's going to be x minus 9 times x minus 1. The problem is, or the difference here, is x times x gives you x squared. We don't want x squared. We want x times x to give us x to the 4th. So what are we going to have to do here? Well, what we're going to have to do here is raise the power of the factors. So whenever you have a problem like this, I just recommend to factor it just like how you know how to factor, and then raise the powers of the factors to meet the problem. And now, if we wanted to write the linear factorization, we could factor those out a little bit more. X minus 3 times x plus 3 times x minus 1 times x plus 1. And now you can see there are 4 factors. They all have a multiplicity of 1 because, again, we're looking at the linear factors. These are not the linear factors, so we can't take these. You can't take that power as the multiplicity. Here's the linear factors. They all have a multiplicity of 1. So therefore, we can write our solution set plus or minus 1, comma, plus or minus 3. All right, on the last example, you can see that we have 4 terms. Now, we can't use the same techniques that we used in the other examples, but we are going to kind of combine a little bit from those first 2 examples. Yes, always look to factor out the GCF if you can. But in this case, they all do not share anything. So therefore, we're not going to be able to do that. The next thing that we're going to want to do, though, is factor out, well, first of all, when you have a subtraction, is group the terms. So we're going to want to group the first 2 terms and the last 2 terms. But we got to be careful because when I say group, I don't want to write it like this, because when you write it like this, what you effectively have just done is you have turned this into a multiplication problem, right? We don't want to change it to a multiplication problem. So what we're going to do is we're just going to rewrite it as 2x cubed, parentheses, plus 3x squared, plus negative 2x minus 3. Okay, so just be careful with how you're using your parentheses here. Instead of subtraction, we're just going to write plus a negative. Now, for each of these expressions, we are going to factor out the GCF. So in this first expression, you can see that they both share an x squared. So you factor out an x squared, you're left with 2x plus 3. Over here, you can see that they share a negative. And again, our goal here is whatever you factor out of this, whatever's left over, we want to be the same as this. So when I factor out a negative 1, so let's just say a plus a negative 1, right, which is really you could just write as minus 1, that's going to leave me with a 2x plus 3. Okay, now you can see I can factor out this 2x plus 3. So I get 0 equals x squared times a 2x plus 3. And, factor that out. And that will be a 2x plus 3, and what's left over? An x squared minus 1. Okay, now we can go ahead and set these both equal to 0. So therefore, again, this is a 2x plus 3, and this is going to be an x squared minus 1 equals 0. So therefore, x equals a negative 3/2, and x equals plus or minus 1. So writing this as a solution set, we'll write was plus or minus 1 and a negative 3/2. And again, these all are going to have a multiplicity of 1. So this is called your factoring by grouping. All right, so this whole process was taking an equation, factoring it down, setting it equal to 0, setting each factor equal to 0, and then solving. All we're going to do now is if I give you the zeros, you're going to set the zeros as a factor equal to 0, raise the factor to its multiplicity, right? If it has a multiplicity of 2, then you take the factor and raise it to that power, and then multiply it out to get your polynomial. And you can see I kind of set these guides out here for you, but it really, again, is just going to come through a step-by-step doing the exact opposite of what we just did. So let me show you how this works. The first one, take all your zeros and then set them equal to x. So we can say x equals 1, x equals negative 1, x equals 2, and x equals 0. Now again, I'm going to go through this first one kind of a little bit slower because obviously once you start seeing patterns, you can kind of pick it up a little bit. So again, you can subtract the 1, right? So therefore you get x minus 1 equals 0. This would be x plus 1 equals 0. This would be x minus 2 equals 0. And again, if you want to play the game, x minus 0 equals 0. Then we apply the multiplicity. Again, remember this is 2, so therefore we're going to raise that power to 2. Again, x minus 0 squared is really just x squared, right? Okay. Now we take our factors, and remember, how did we get these factors? That was from the zero product property. We take every factor that's equal to 0 and set them by themselves equal to 0. So now all we're going to simply do is say, all right, each of these came from the x squared minus 2 times x squared, right? The product of factors equal to 0, and then you did zero product property. So to write the equation, I'm just going to say y or f of x or whatever may be the case. And now we just need to multiply these out. Now, typically, I like to multiply binomials by each other first, especially when you have difference of two squares. That's going to be an x squared minus 1. That was easy. Here, you're going to apply a little distributive property. So this becomes a what? X cubed minus 2x squared. And then you just have a binomial times a binomial, and you can apply the distributive property or FOIL. Let's just kind of work this one out. X squared times x cubed times x squared is going to be x to the 5th. This becomes a negative 2x to the 4th minus x cubed, and then plus 2x squared. And there you go. Next example, again, we have two zeros here, so we'll both with multiplicity of 2. Now this one we have a fraction, and it's kind of important to understand where the fraction came from. So remember, look at this fraction. If I gave you this fraction, it didn't come from x plus 3/2. It could have, but the problem with that is then you're going to be dealing with a polynomials that has coefficients of fractions. We don't want that. What we want to do is use inverse operations to get it so therefore it's with integer coefficients. So the way to do that is we're, again, set them both equal to 0. Instead of subtracting the 2/3, multiply by 3. So this would be x plus 2 equals 0. And this is 3x equals 2. And then divide by, and then subtract the 2. So therefore, you'd have x plus 2 equals 0. And 3x minus 2 equals 0. Do you see how I preserve the integers here? I'm not using fractions because, again, these are my two factors. But again, these are two factors that have a multiplicity of 2, right? So I'll say 0 equals x plus 2 quantity squared times 3x minus 2 quantity squared. Now, all I need to do to write the equation is I just need to multiply these out. So remember, when you have a binomial squared, hopefully you kind of like practice this. You don't need to use binomial expansion, but hopefully you recognize that, something that we did in the last lecture, that this is going to be x squared plus 2 times the sum of 2 times x, which is 4x, plus 4. Here, that is going to be a 3x times 3x is a 9x squared. And then negative 2 times 3x is negative 6 times 2, which is negative 12x. And then plus 4. Now we have a trinomial times a trinomial. Now you can do what we did over here, which is basically applying distributive property. But in my opinion, that gets kind of confusing. So what I prefer to do is do what we call the box method. And basically the box method is taking each of your binomials and putting them on the side of a box. Because when you multiply to find the area, or when you multiply, basically what you're doing is you are finding the area of a rectangle. So we have x squared. Now it gets a little bit more confusing when you're dealing with variables and expressions rather than just, the side lengths of a rectangle. But it works exactly the same. And the reason why I like using the box method is it also organizes all this stuff. So again, all you're going to do is find length times width. That is the area. And then if you add up all the areas of this box, that will give you your polynomial. So here we have 9x to the 4th. Here we're going to have a negative 12x cubed. X squared times 4 is a 4x squared. This becomes a 36x cubed. This is negative, 24, so that'd be a negative 48 x squared. This is a 16x. This is a 36x squared. Negative 4 times 8, so that's going to be, again, another negative 48 x, and then this is a 16. And again, the cool thing here is that these diagonals, you can see, are all like terms. So my final equation is y equals, 9x to the 4th, that's the highest power. Here, this is going to be a plus a 24x cubed. That is going to be a positive 40, so that's going to be negative 8x squared. This is going to be a negative 32x plus 16. And again, these can be very, very confusing and difficult, and it's very possible and very easy for students to make mistakes. So that's why I like using the box method to keep everything through there. All right, the last example, or next example, again, now this one tells us what our leading coefficient is. And this is kind of like interesting as well as important. I'm not really sure why I put the leading coefficient of 1, but sometimes we may have like different leading coefficients. And, I don't know. Let's just maybe change this to like 10 because that's not really interesting to have a leading coefficient of 1. Oh, I see what it is. That's not going to have a leading coefficient of 1. That's why. All right, so let's go ahead and go through this problem. So again, we have x equals 0, x equals negative 1/2, and x equals negative 3. Now again, here we have multiplicity of 3, right? So that's really going to be x cubed. You can, equal 0. Here, I'm going to multiply by 2 and then add the 1, right? So I have a 2x plus 1 equals 0. And then here I have an x plus 3 equals 0. Now, when I multiply these all out, I get y equals x cubed times 2x plus 1 times x plus 3. Multiplying these two out, I get y equals x cubed. Let's see here. That's going to be a 2x squared. That's going to be a 6x. That's going to be x. So that'd be plus a 7x plus 3. And then when I distribute here, I get a 2x to the 5th plus 7x to the 4th plus 3x cubed. Okay. Now the problem is the equation says you have to have a leading coefficient of 1. Well, my leading coefficient is 2. So what do? Well, the important thing is, remember, if you multiply by a scalar, that's not changing the zeros. All multiplying by a scalar is going to do is stretch and compress your polynomial, right? Because again, like we talked about this, it doesn't matter if this was 2x cubed or what if it was 1/2 x cubed. The zeros would still be the same. So all I need to simply do is just multiply my polynomial by 1/2. Because that 1/2, when I distribute that, is now going to make that coefficient 1. So I have a final polynomial, which is x to the 5th plus a 7/2 x to the 4th plus a 3/2 x cubed. Okay, so again, remember you can multiply by a scalar because that is not going to change your zeros. All it's going to do is vertically stretch or compress the graph. All right, the last example here is it goes through these it has these zeros, but then it also goes through point 0, 1. And again, this one's kind of related to this problem. We need to kind of do a little bit more thinking than just finding the zeros. But first, let's go ahead and find the polynomial based on, what it is we know here. So in this case, we have, x equals, let's see, if I have plus or minus 1 and x equals plus or minus 2. Now, hopefully you recognize that those are going to come from the difference of two squares. So this is really x squared is equal to 1. X squared is going to equal, This is really x squared minus 1 equals 0. And this one's x squared minus 4 is equal to 0, right? Those are going to be your zeros. And therefore I have an equation y equals x squared minus 1 times x squared minus 4. And then you multiply those out and you get x to the 4th minus, let's see, that's going to be a positive 4x, negative 4x. That'd be a negative 5x squared plus 4. Okay. Now again, though, remember it has to go through this point. Now, the only thing else that we can do to this problem would be, again, change the scalar, right? We can't change the zeros. These have to give us the zeros. The only thing, though, that we can change is giving it a scalar. So what we can do is say, all right, what if that scalar is k? We don't know what that scalar is. But we know that this cannot change because this function gives us those zeros, and we have to have those zeros. But let's say we need to add a scalar that's going to satisfy this. Now again, what does the 0.01 give us? That gives us our point xy. So I can plug 0 in for x and 1 in for y. So what happens when I do that, let's figure out what I get. I get 0 squared minus 5 times 0 squared plus 4. 1 equals 4k. Divide by 4, divide by 4, and I get k equals 1/4. So therefore, again, I have a new equation of y equals 1/4 parentheses x squared minus, that's not x squared. That's x to the 4th. That's supposed to be x to the 4th too. So x to the 4th minus 5x squared plus 4. And then if you want to distribute that, because that's what your question you need, then that would be a 1/4 x to the 4th minus 5/4 x squared plus 1. So there you go, ladies and gentlemen. That is how you write the equation when given the zeros and the multiplicity, as well as how you find the real rational zeros by using factoring. Hopefully this was helpful. Go ahead and get started on the quick quiz, and I'll look forward to seeing you in the next video. Cheers.